Okay, this video is meant to be a quick proof of this analytical formula that we said is relatively general and applies to all linear regression um, problems. Linear regression in the sense that the unknowns that you're solving for are linear in the equation that you're trying to fit to the data. That's what we mean by linear regression here, at least. Okay, so how do we derive this formula mathematically? And this is actually the proof. The proof is not super important, but if you want to get a flavor of how these proofs work, I suppose this is an introduction. And before I do the proof, I'm going to do a quick linear algebra and calculus aside for essentially doing matrix calculus, because we're going to be dealing with matrices and differentiating expressions involving matrices and so on. Okay, so let me just do a very quick summary of key things that we need for this proof. Okay, and I'm not going to prove these little details, but I'm just going to state them, and maybe we'll do a linear algebra um, lecture separately for a broader introduction to linear algebra just for the purposes of this course. Okay, so if you have two matrices, A and B, that are compatible for matrix multiplication, and you have A times B, and then you take the transpose of that product, A times B, it turns out that the transpose of that product is actually B transpose A transpose, okay? Not A transpose B transpose, because A transpose B transpose might not even be legal. Okay, and then similarly, A, B, C, the whole transpose is C transpose, B transpose, A transpose, etc. Okay, so this is a super important thing because we're going to be taking transposes of products all the time for this proof. So that's piece number one that we will need. And you can try to prove this for very simple, maybe 2 by 2 matrices or something like that. Okay, now if you have n scalar variables, p1, p2, p3, etc., or sort of more abstractly, if p belongs to the set Rn times 1 or Rn, we can construct a linear function of p. So f is a linear function of p. What do we mean by that? It is a function that is some constant times p1, some constant times p2, etc., until pn. Okay, so that's a linear function of p. Sometimes we might also add a constant c naught, a constant term that does not depend on the p's. People might call that a linear function as well, and we would as well. And sometimes people might differentiate this function with something that has a constant term. The constant term version of the function might be called an affine function, A-F-F-I-N-E. Okay, so that's called a linear function. And you can write this linear function that has the sum as sort of a matrix expression where F equals C transpose P, where C is this array and P is this array, okay? And then you go C transpose, you get this to be a row matrix instead of a column matrix, and then you do this matrix multiplication, you get this single scalar expression, okay? So that's a linear function of P. Okay, now, if you have a function of n variables, you can define what's called a gradient of that function. Okay, so the gradient of a function is the set of partial derivatives. If you have a function f, which is a function of p variables, the gradient is basically partial f, partial p1, partial f, partial p2, etc., till partial f, partial pn. And this is a general definition. It doesn't have to do with this linear function. For any function f, this is called the gradient, this expression, okay? Now, of course, if you take this particular linear function of p, potentially including a constant c naught, if you take the gradient of f with respect to p, you can compute the partial derivatives of f with respect to p, and of course, they're going to be c1. If you differentiate this expression with respect to p1, that's just going to be c1. With respect to p2, it's going to be c2, etc., right? So the gradient of f with respect to p, denoted like this, is going to be c1, c2 till cn. And that's just going to be equal to the array C. Okay, so the gradient of C transpose P is C. Okay, it's just like the derivative of the number 5 times x with respect to x equals 5, the number 5. Similarly, C transpose P with respect to P is C. Okay, it's not C transpose, it's actually C. Okay, so that's super important because we're going to be taking the gradients of functions all the time in the proof in a minute, well, at least once. Now, why do we care about the gradient of a function? Because whenever you're doing minimization or maximization, when you're trying to minimize a function or maximize a function, what do? You take the derivative of the function and set it equal to 0, at least if the function is unconstrained. So we're going to do a whole lecture or two on optimization or minimization and maximization, but at sort of a high level, if you have at least a univariate function, a function of one variable, and there are no constraints, and you want to minimize that function, you try to find the derivative and set it equal to 0, right? So this is what you learned in your undergraduate calculus class. Now, if you have a function of many variables, f of p1, p2, p3, and there are no constraints on p1, p2, p3, etc., they could take any values, then it turns out the necessary conditions for minimizing f is that the gradient of f equal to 0. There are some caveats here which I'm not going to talk about just now because we're going to do a whole lecture on optimization, but at least for the purposes of the next page of this proof, what we're going to do is set the gradient equal to 0, okay? So in other words, we want to take the partial derivative of the function f with respect to each of the variables and set it equal to 0, and it turns out that that will give us the minimum of that function. Again, like I said, there are some caveats which I'm glossing over here, which will be clearer in the optimization lectures. Okay, so that's for a linear function. The gradient is just the coefficients. If you have a quadratic function of f in P, you can actually write that function in the following form. F equals some constant, f naught, and then some term that is linear in P, and then some term that is quadratic in P. Okay, so the quadratic term is actually half P transpose HP. You can, if you just expand this out, you will notice that these terms look like P1 square, H11, P1 square, H12, P1, P2, H22, P2 square, etc. So just try to have a 2 by 2 H matrix. Okay, so here H is an n by n matrix. If you have n elements in P, H is going to be an n by n matrix. So just take H equals a 2 by 2 matrix, H11, H12, H21, H22, and then P equals P1 and P2, and then expand this thing out and see what the expression looks like. Okay, so and you'll notice that it's a quadratic expression. And if you want to take the gradient of that quadratic expression, then of course this is a constant. So taking the derivative of that is 0. This thing is a linear expression in P. Gradient of that is just C, as we saw before. And this quadratic expression in P, it turns out that the gradient is actually H times P. Okay. H is sometimes called the Hessian matrix. It's actually the matrix of partial derivatives of this function f with respect to P. Okay, so H is the matrix of second partial derivatives, I meant to say. Matrix of second partial derivatives. In other words, H11 is going to be d square f by d P1 square. H12 is going to be d squared f by dp1 dp2, right? So the second partial derivative of h with respect to p1, p2, p3, p4, etc. until pn, all possible combinations. You make a matrix of that. That's basically going to be h. Okay, so that's going to be the linear algebra and calculus preliminaries for the proof on the next page. Okay.